Hello there. Welcome to the session 3 of this unit. Let's look at the objectives. So our first objective here is to state the Fermat's principle as applied to the propagation of light. Derives the laws of reflection and refraction using the Fermat's principles. And also state the applications of this Fermat's principle. So there is some statement that Fermat made in his time. And first, he stated that the actual path between two points, that's A and B, taken by a beam of light at the point that is traversed in the least time. 2. Light travels between 2 points along the path that requires the least time compared to another nearby path. And lastly, the path between 2 points taken by a ray of light leaves the optical path stationary under variations in a family of nearby points. So let me explain this. In case that this place is B, is a pool, and let's say someone is at A, and you are being sent to give something to the person, there's no need for you to use this path by going here and coming to B. We are saying that there's a short path that you can take, and that is from A straight to B. We are going to use this principle to deduce the formulas that we already have in reflection and in refraction, and I hope we will enjoy it. I believe that we are all very familiar with this schematic diagram. Don't be confused about the A, the X, the D minus X, and the B. Let's focus on this. And we know that the one law of reflection is the incident ray, the reflected ray, and the normal. The normal at the point of incidence all lie on the same plane mirror. And we also know that the angle of incidence is always equal to the angle of reflection. Right now, let's use Fermat to deduce this formula. And the formula that we were able to deduce from the law of reflection is the angle of incidence is always equal to the angle of reflection. Now, let's consider this part. When you finish, we'll consider the other part. So, let's take this place to the end here to be our A. And let's take this part here to here to be our small b. And let's take the distance from the big A here to the point of incidence to be x. And let's take the path here, the direct path, that is the path from A to B here to be D. Because we have this place to be x and we have this place to be D, automatically when you subtract this x from D, we are going to get the path from the point that we have here to our big B. I hope this is clear. This will help us understand what we actually have here. I hope you are very familiar with electrokinematics, where we have our velocity v to be always equal to distance d over what? Distance or speed over time, right? So here, let's make the time the subject, where we have t right now to be equal to what? Our distance here to be d over what? Velocity v. Here, our distance here right now is going to be this long part here. That is from the big A to the point here. And that is our incident ray. And from Pythagoras theory, in case we want to find this particular distance, we just have to find the square root of the square root of a and also the square root of x. And that is what we have here. Here, this whole thing represented by what? D. So we have our a squared here, and our s squared here, and our v here, and our t to be here. The same thing applies to the other side, where we have our reflected ray. We want to find the reflected ray, right? And from Pythagoras theory, we have the square root of the square root of b, which is here, and the square root of the whole of d minus x, which is here. And we have our v here, but this time it's a v prime to differentiate it with this one. Is that okay? So this whole thing is the time for the direct path. So for the time from A to B. Let's find the derivative of this time, which I know some of you are already familiar with. So finding the derivative of t with respect to x. So the square root of a squared plus x squared can be presented here as a squared plus x squared. Kindly forgive me because I'm using a mouse pad, and the square root can be represented by 1 over 2 here. And anytime you find the derivative of something like this, the 1 over 2 comes down here. We enter into the bracket, differentiate what we have here. This place is going to be a constant because it is with respect to x. And when we find the derivative of this one, we are going to get 2x. So 1 over 2 times 2x, right? Times again a squared plus x squared. But because we are finding the differentiation of it, we have to subtract 1 from here so that we get negative 1 over 2. So after finding the differentiation of this, only what we have at the top here, this is what we get. So that these 2 here cancel these 2, and we get x multiplying our a squared plus x squared. In the bracket, outside the bracket, we have negative 1 over 2 at the top here as the exponential, right? This is what we get. And because we have negative 1 over 2 at the top here, it can be presented as x. This one is an equal to sign here. So I think you should be following my voice more. So that we have a squared plus x squared. Because there's a negative here, it can come down here so that we get 1 over 2 here. So the negative here, bring it as a denominator, right? And we can clean this thing and just make it square root. So let me just clean it and make it a square root. I hope you understand. And that is what we have here. So this one, only this one, is for finding the differentiation of what we have at the numerator. And when you finish, you bring this vein attached here. I hope you understand. So I'll leave this one for you to find out how the differentiation of this one, the top, only the numerator, works for us to be able to get only this. Now we know that sine is always equal to what? Opposite over what? Hypotenuse. And now let's look at this theta here. Our opposite is here, and our hypotenuse is what? Is here. Look at what we have here. we have our opposite to be x, which is here and is the same as what we have here, ending here, right? And our hypotenuse is what we just calculated for, and is going to be our denominator here, right? Because this part from Pythagoras theory is what? The square root of the square root of a and the square root of x. So we can present the whole of what we have here. Let me use a different color. The whole of what we have here to be what? Sine theta 1. The same as we can present the whole of what we have here as theta 2. Now look, in case that we have the speed of light that is traveling from the incident and from the incident ray and also from the reflected ray, we can say that v here is equal to what? This particular v, which is can be cancelled out, and one of this theta here is being sent to the other side, and we are going to get something like this. But should in case we have for parallel rays or small angles, our theta, sine theta equals tan theta, and which is also equal to what? Theta, which is going to make theta 1 to be equal to what? Theta 2. And this is already what we have in our law of reflection, where we have theta 1 to be equal to theta 2, or the angle of incident to be equal to the angle of what? Reflection. Okay, so for here, we are going to use the same thing, the same Fermat's principle to calculate or to prove for the refraction law. That is n1 sine theta 1 equals n2 sine theta 2. We know that from our kinematics, velocity is equal to what? Speed over time. And in case we want to make t the subject, the time the subject is going to be the speed over velocity. And if we are finding the time traveled from P here to Q here, because they have different distances, that's our R1 and R2, and supposedly different velocities, that is V2 and V1 and V2, we are going to have time here to be equal to our R1 over V1 plus R2 over V2. Let's go to our basic Pythagoras theory again, where we have R1 to be equal to the square root of a squared and x squared, which is going to give us this. The same thing implies here for the R2, where we have our square root of b squared here, this b, and d minus x squared. Don't be confused about what we have at the denominator here. You remember that we wrote a formula, or I explained a formula earlier, where we had the refractive index n to be equal to c over v, where the c here was the speed of light and the v here was the speed of light in the vacuum, in a medium or any material, and the c here is the speed of light in a vacuum. That's 3 times 10 to the power 8. So in case we make v here the subject, we are going to get c over n, and that is what we have here. And because it's a different refractive index for medium 1 and medium 2, we have n1 and n2. So I'm going to leave the rest for you to do, and I'm going to use the same procedure we used for the previous one to prove for this. You'll find the derivative, and when you finish, you use the angle to compare, then you get your answer. Good luck with this. Let's look at the applications of Fermat's principle. And one common application is where one common application is research by some scientists has shown that ants behave the same way as light does when traveling through a different medium. Both paths obeys Fermat's principle at least time, taking the fastest route rather than the most direct one. And also, the principle is also used intuitively by humans when a lifeguard has to get a swimmer as quickly as possible in order to prevent the swimmer from drowning, as I explained earlier.